First page is good? First page is as good as it's going to get. All right, let's do second page. Wait, there were 2 pages, weren't there? Whew. Okay, yes. Onward. So we kind of did one of the problems like what I was hoping you'd do on the second page already, because I went through the trouble of doing all this mess. So is there anything else? Do you understand the process? You find your eigenvalues, find your eigenvectors. I should leave that in there so I don't forget. And I'm going to take this off because it's getting a little warm in here. All right, so second page is good? Well, as good as it's going to get. All right, so today's lesson, I know we're skipping that. Look, no quiz on the list here. So I already told you what we're doing for the week. And I'll make sure that there's material online. Here, I better put this on my list as well. So we need to have the DiffEq practice test online as soon as possible. List of things to do when I get back to my office. Are there presentations today for the there is? Engineering. It's tomorrow? Yeah. Okay, someone said they had, maybe it was the CAD students, those youngsters. Okay, they were all nervous in Calc 2. You have to do it today? Oh, exciting. You're going to do a CAD presentation? All right, good. All right, so what we're doing today is we're going to just go over some special cases of what could happen, and you already know what's going to happen here, I think. For example, repeated eigenvalues. Repeated eigenvalues, can you take a guess? I'll bet you can as to what's going to happen. If you have a repeated eigenvalue, you just throw an extra t in there, just like you do with a second order differential equation. Second order differential equations, the solution techniques are very similar to systems of differential equations. So if you got one, the other one will be pretty easy. Zero eigenvalues, that's a little bit different, so we'll take a look at that one as well. So let's first of all take a look at a situation with repeated eigenvalues. You might say, what are the eigenvalues for this thing? Well, we can do this, I'm confident. Yeah, the issue here, though, is that if you have repeated eigenvalues, you have only one straight line solution. You remember that diagram I showed you with all those little arrows? And there were 2 different directions that the lines kind of went off in 2 different directions. Well, with a repeated eigenvalue, you only get one such vector, one place where you're going straight line. Everything else is going to be a spiral or a, I've got some words there that we haven't gone over. Spiral, source, or sink. You can ignore that. So what I'd like to do is actually do this. So here, let's see, can I get rid of the words? There it is. So we're going to do this one. In fact, I don't want to do this on here. I'm going to do it over on Notability. Hold on a minute. Put it in there. There you go. Hopefully this isn't too challenging for you now that you've done a few of these. So the first things first, we're going to do this. Whoops. -1, -4 minus lambda. And this is the determinant of this stuff. There we go. So what do we got here? This is going to be -2 minus lambda, -4 minus lambda, +1. Hopefully I can do my math right this time. We're going to find out. So that will equal lambda squared plus 6 lambda plus 9. Double check, because I don't trust my algebra at this point. So look all right? Someone's checking. All right, you know what my mistake is? I should have just made you do it. So you can do the next step. Factor that for me so that I don't have to, because apparently I'm not doing as good. So Jackson, what are the factors of this thing? All right, so it's lambda plus 3, lambda plus 3. And then what happens is that you get lambda equals -3, lambda equals -3. So when this sort of thing happens, we have to do this special case where we're going to have to deal with two separate, because you need two separate solutions for this thing. So here's what's going to happen is that one of your solutions will just be e to the -3t. We'll get to the whole eigenvector thing in a minute. And then the other solution will be t e to the -3t. So you have these two separate solutions that we're going to have to deal with. Let's go ahead and find the first eigenvalue. So this is for lambda. Let me just write this down. Lambda equals -3. And then this is the duplicate over on the right. We'll get to that. That's special. So that's going to be a little bit more challenging to get. But go ahead and see if you can find the eigenvector for the eigenvalue -3. So I'll give you a minute and see if you can work that one out. All right, let's see how we're doing this. Let's see, what do we got here? Triton. What kind of equation am I gonna do here? So remember, here's my lambda. I'll just get it set up, but you tell me what to put in that matrix there.
Okay, so you're gonna do -2 minus that lambda.
Okay, so that's gonna be 1.
1, 1, -1, negative.
All right, beautiful. So we got that. So this gives us two equations with two unknowns, but they happen to be the same equation. Darren, what's one of the two equations? It doesn't matter which one.
X plus y.
Yeah. So x plus y equals 0 is one of them. The other one, by the way, is -x minus y equals 0. So it's the same equation, essentially, just negate the negative. All right, Avin, I need an x and a y that satisfy this. What x and y do you like? That works. So you could do this sort of thing, that y equals -x, and you say, okay, x equals 1, y equals -1, and that's going to be my eigenvector for this. So let me just put this up here so that we can remember v1 is equal to, what did we say? 1, -1? 1, -1. Now, as far as the second eigenvector goes, the second eigenvector, it's not really an eigenvector, but we need something that's going to stand in for an eigenvector for this piece of the solution. So this is going to be corresponding with that piece. The other one is going to correspond with this piece here. And the way that's going to look is we're going to take this equation right here. Let's see if I can write it down. You have a minus lambda I times v1 is equal to 0. So that's the thing that we just solved. That's this right here. So I'll write down the expression, but then in practice, what we do, it's pretty straightforward. In fact, I have to get rid of that arrow because it's in my way. There. So that's that. That's just, you're just subtracting off the -3 and then solving for x and y. That's it. So the way you get your second vector in a double eigenvalue situation is you solve this. So notice that to get the second Clash of Clans. We didn't bring oatmeal cream pies for the class.
No, I did not.
It's still blinking.
Yeah, it's distracting.
Is that better? All right, so solve that. Oh no, here, I'll cover it up. I'll cover it up in a minute. Okay, so here, solve this. There we go. Okay, so solve that. Notice the difference. Instead of having 0, 0, I put the first vector in as the answer instead of 0, 0. So down there, I would scroll. Oh, thought it was done. It's done. If only I had tape. It's all right. That's not good. Okay, yeah, so it's the same as this. Can I put something? Can I hang something over this? It would stay. Oh, is there tape? That'd be exciting. Watch the moment I get it fixed.
Maybe while your head's up there, it'll go off.
That'd be great. Just don't look. Don't look.
I'll just stand up there.
That's okay. It's a tip that I would, I don't even have a stapler anymore. Okay. Okay, so anyway, get her done. Oh, that went out on the stream. Wait, is anyone missing today? I don't even need to be streaming. Or, is that right? Everyone's here. Oh, what? These people?
That's everybody that's watching.
Oh yeah, if anyone's watching, yeah, the world has ended. Well, that's exciting. Okay, so let's do this. Okay. Is there no tape here? Can I hang this?
That's like nice.
Amazing. Okay, so let's get it done. So what do we have here? 1x plus 1y equals 1, and negative 1x minus 1y is negative 1. Same equation, right? It'll always work out that way, that it's the same equation. And so we have x is equal to 1 minus y, either one simplifies to this. So we have this choice again. You can pick whatever you want for x or y, and we'll figure out what the other one is. Let me find a volunteer. I know you all want to volunteer for this one because all you gotta do is pick. But Clayton, what number would you like for y?
0.
0? Okay, that's a good one. So if y is 0, then x is 1, right? So that's the second vector, but it's not really an eigenvector. So we're going to just put this over here, and that's going to equal 1, 0. Okay, so now for the confusing part. Not that this hasn't been confusing to begin with, but when you have a double eigenvalue, here's how the solution looks. We have C1 times e to the lambda, because there's only one lambda, so I don't have to say lambda 1 or lambda 2. So e to the lambda t times v1. And then you're going to do C2, and then you've got this big nasty thing that we have to do. I know. So we have, let's see, e to the lambda t times t. Sorry, I should have put the t out front. So you throw an extra t in there, and then you put a v1 plus e to the lambda t times v2. I know it seems super confusing, but let me clean this up just a bit. Sorry. Cleaning. E to the lambda t. So it's hard to remember all of this stuff. It's in your book somewhere, but essentially what you're doing here is you've got the C1. This makes sense. But then this thing, what this is doing is, you know that the derivative of t e to the lambda t, the derivative of that has this as part of it. Because there's a double root, then this will be a solution to the original differential equation, but you want to correct for the fact that the derivative of this has this. And so that's why you have both of those. So the V1 goes with the t, and then the V2 goes with the non-V, or the non-T. So let's put it all together for this one. Give me a sec here. C1 times, where is it? Where's my original eigenvector? 1, negative 1, times e to the, was it negative 3? Okay, negative 3t plus c2 times t e to the negative 3t times 1, negative 1. We'll clean this up, don't worry. Plus e to the negative 3t times my new eigenvector, which isn't really an eigenvector. What was it? 0, 1, 0. And you might notice that there are a variety of different vectors that would have worked for this, and that's okay. Okay, so let me make this look a little prettier. So we have c1 e to the negative 3t for x, plus c2 t e to the negative 3t plus c2 e to the negative 3t. So that's my x. Notice that I'm doing this roller coaster thing. If you want to think of it, starting here, you go up, and then up, and up. And then the y, we go down. Negative c1 e to the negative 3t minus c2t e to the negative 3t. And that's it. Oh. Well, let me see. What's next? I don't know. Are there concerns, questions, worries? Let me see how far we need to get to some good stuff here. We can do that section now. Yeah, let's just skip the 0 eigenvalues. Give me a sec. And we will go right on to complex eigenvalues. And I know you're looking forward to this, aren't you? Oh, wait, we already got 0. Just a minute. Where's my complex? Is this it? That's the same thing. Hold on a minute. Yeah, I thought I had it up here. Just a minute. Systems? Oh, here it is. Oh, there it is. Complex eigenvalues. Okay, so what happens with complex eigenvalues? I bet you can guess what's going to happen with complex eigenvalues. In fact, let's just get to a system that has complex eigenvalues. How about this one? No, not, well, it doesn't matter. Yeah, this one will work. You have an initial value there, but this will be a good example. So we'll get to the what happens in just a minute, but and I suspect that you know what's about to happen, but let's go ahead and do this. So first things first, I need to write this down. So 2 minus lambda, 8, negative 1, and negative 2 minus lambda. And you're doing the determinant of that, and that should equal 0. So take a minute, see if you can solve that, and I'll find a volunteer to help me out. Well, Gabe, were you able to do the determinant of this stuff?
So the m squared, and then the middle term cancels out, right?
That's correct.
And then the last term is just minus 4.
Excellent.
And then minus negative 8.
Excellent. Very good. Yeah, so another, you might notice that this is the difference of two squares. So 2 minus lambda, negative 2 minus lambda. But anyway, there it is. So then we get lambda squared plus 4 equals 0. All is well so far, right? We're all happy. And then we have to actually compute the eigenvalues. Jason, what do you get for the actual eigenvalues? 2i? Is that the only one? Here, I'll give you a hint. We have lambda squared equals -4. And you did the square root of both sides. And when you do the square root of a square, you get something special. You get a positive and a minus. Yeah, very good. Plus and minus, very good. So there it is. So you have two eigenvalues, plus and minus. Now, if you had to guess, what is this going to look like? It's not going to be e to the whatever. It's going to be a cosine and a sine. Yeah, it's going to be a cosine and a sine is what we're going to have here. So how do we deal with this? Well, whenever you have cosines and sines, the way that this is going to shake out is we're going to have to come up with some eigenvectors, and the eigenvectors are actually going to be complex eigenvectors. So let's see, we can do this. I'm confident. So let's take this thing, and we're going to start with lambda is equal to 2i. Let's go ahead and work this through. So we have this that we're supposed to do. 2 minus 2i, 8, -1, -2 minus 2i. X and y, 0, 0. This looks scary. I'm going to persevere, though, because I care. So let's go ahead and do this. Aaron, what's the top line? Just, you don't have to do both equations. Just what's that line give you for an equation?
You get 2x minus 2xi.
Okay.
And then plus -2 minus 2i.
Oh, no, no, no. This is, yeah, we're just doing this times.
Yeah, so it'll be 8.
Yeah, 8. Whoops. Darn it. Why did it move on me? 8y. And what does that equal? Okay, very good. Let me see if I can clean this up. It moved on me and messed up my writing. It's a little better. PowerPoint does not behave well with the iPad. All right, so far so good. We got that one. And then we've got another one. Let's see if we can do the other one. Clayton, what would the other equation be?
-x plus -2 minus 2i.
And that equals 0 as well. Now, in the past, these equations have always been so obviously the same that it was easy to see that one was a multiple of the other. That's not the case here, is it? It doesn't look at all alike. Well, let me show you that these are in fact the same, and then we'll actually solve one of them. Generally, if you've done your math right, those will be the same equation, even though they don't look at all alike. So let's see if we can demonstrate this for you. You know what I'll do is I'll do this. I'm going to take this one and solve for x. There. How's that? So x is equal to -2 minus 2i times y. So that's going to be the, so we'll use that one. And then what we could do is we could just solve this one for, should we solve that for y? Yeah, let's solve that one for y. So this is y is equal to -2 minus 2i x over 8. Now, to show that these are exactly the same equation, you could take one of those, plug it into the other one, and what you should get is either x equals x or y equals y, right? So let's double check. I guess I'll take this, plug it in here for y. So x should equal -2 minus 2i times the negative of 2 minus 2i times x over 8. This looks like it's going to be complicated, but I think I'll persevere. It'll be okay. So let's see, this is going to be 2 plus 2i times 2 minus 2i times x all over 8. Now let me explain what I did is I took this negative and I said, hey, it'd be more convenient to multiply that -1 times this than to multiply it by this. That'll get rid of a bunch of negatives. So that's why this became positive. Now I'm going to multiply all that mess together, and that gives me this. Let's see, this is 4 plus 4 over 8. And sure enough, x is equal to x. So those check out. Those are the same equation. So you can pick whichever one you like better, and then we'll set up our equation, or our vector this way. So I'm going to take that one, and my vector ends up being, oh, I should have written a little bit more. I'm going to let y equal 1, which means x is equal to -2 minus 2i. I know, this is getting kind of messy. I should have gone over to notability. But let's see what we're going to do with these eigenvectors now that we've got one. So the deal is that if you have your eigenvectors, then what you can do is you can take those, oh, I should mention, where is it? Where is it? Where'd it go? Oh, there it is. Okay, so I should mention that that's one of the eigenvectors. The other one, so that was the one that corresponds with this, lambda equals 2i. If you did the same thing for lambda equals -2i, you would get this. So I don't know if you noticed the relationship. And the reason why this relationship exists is because if I change the -2i's to +2i's and did the same thing with those two equations, what I would get is exactly the opposite. The I becomes positive here and here, and that's the only thing that would change, is this would be positive instead of negative. So anyway, we have that as our framework. Now, before we get all bent out of shapes, thinking that we're going to mess with the eigenvalue, eigenvectors, and Euler's formula, let's just cut to the chase here and say that once you have one eigenvalue, if it's complex, and one eigenvector, that's all you need for this solution. Because the other one is just the opposite or the conjugate. So what you do is you put these things together, and I'm going to do this for you here. You put these together into this solution, and the solution is going to involve the eigenvector written in complex form. So here, might be easier if I actually just do it. So let's take that green. I'm sick of using PowerPoint. Let me just go over here to Notability. Hold on a sec. Put this baby in here. That's better. Okay. So I'm going to take this eigenvector right here. Whoops. That one there. Let me rewrite it. Lambda equals 2i. V1 is equal to -2 minus 2i and 1. So this eigenvector could be thought of like this. So notice that that vector, I could separate it into the real and imaginary pieces. And now all that's left to be done is to take those two pieces and build the solution out of those two pieces. So the way this looks is you end up with constant 1. Let's see. I want to make sure I get this right. So give me a sec. Go back here. Oh, that wasn't right. Well, might as well discard things. Okay, so we've got those two vectors. We got x1, x2. Where's my example? That's not helpful. Okay, there it is. Here we go. 2, 2, 2, 2, 2, imaginary. Yeah, you do the plus and then the minus. Okay. Oh, I guess this is the solution right here, but we'll go back here. So we have C1 times negative 2, 1 times the cosine of 2t. So notice that gives you the cosine of 2t plus negative 2, 0 times the sine of 2t. So think of it as you've got your positive, or your real part corresponds with cosine, imaginary corresponds with sine, and then you add to this plus C2 times negative 2, 1 times the cosine, 2t, minus negative 2, 0 times the sine of 2t. Sorry, this is a mess. Let me go back to the PowerPoint. We'll just put this up there so you can see it in all of its glory. So here's the general solution. So just to explain where it came from, we have the constant, we have the real part of the eigenvector times the cosine, the imaginary part of the eigenvector times the sine, and then, oh, I messed up. I should have switched it around. Then you have C2 times the imaginary part times the cosine, and then the real part times the sine. So let me just go fix that back here. Not that anyone really cares. This should be negative 2, 0, negative 2, 1. You might worry that I have negative 2, 0, and negative 2, 1 here, and it's the opposite over here. But it doesn't matter because the constants, for the PowerPoint, when your book came up with these eigenvectors, they just did a little different way of doing it. They chose negative 1 for the y value, whereas we chose 1. It still works out to be the same thing. I mean, up to a constant, because the constants will eat the negatives, as Darren likes to say. All right, let's see. So why do we care about this? Well, it's pretty much time to finish. So we really can't do that much more other than to say that if you were to graph these solutions, you get these nice ovals. They're beautiful. I don't know. I'm disappointed that we can't do more with this section, but let's see if we can come up with some homework. So here's the homework. Wait, do I have homework in the PowerPoint? I don't. So we're just going to do it this way. Let's just pick 4 problems. 2 of them are repeated eigenvalues. So this is page 353, section 8.2. And it's going to be numbers 21 and 23. Those look good. Nice odd numbers for you. And then 35 and 37. So try those and we'll do our best. Hopefully they won't have a fire alarm. Oh, look, it stopped blinking. Probably stopped blinking the moment I finally figured out how to block it. So, and hopefully I'll have something. I've got it on my list here. It's, yes. Oh, I don't have it on my list. Let me put it on my list to put a practice test just to make sure there is something.
25 or 26?
That is a 30, 21, 23, 35, 36.
35, 37.
37, sorry. Yeah, 21, 23, 35, 37.